All right, this is now the second part of lecture 8, and we're going to talk about property subsets and set partitions. However, before we go on sets, we're going to do a review problem on proofs. Okay, so here is to provide an indirect proof by contradiction to show that for all integer a, b, and c, if a squared plus b squared is equal to c squared, then a or b is even. Okay, so this is not the same proposition we have proved in the last actual recitation, which said that if c is even, then both a and b is even. Okay, so this is a slightly different problem. So this is where you can pause the problem and try to solve this on your own. And I'm going to go over the proof in the next slide. Okay, so when we talk about proof by contradiction, you again want to assume there exists a counterexample. Okay, and then you want to prove that counterexample leads to a contradiction. So a counterexample doesn't exist. Therefore, the original statement is true. Okay, so this is my sketch. Suppose counterexample exists. Okay, so whenever we think about a counterexample, if we have statement P implies Q, a counterexample is P and not Q. Okay, so what is my P? P is a squared plus b squared is equal to c squared, and Q is a or b is even. So then P and not Q is a squared, b squared is equal to c squared. This is P and not Q. That means not a or b is even. So a is even or b is even. So this is my sketch. This means a is odd and b is odd. Okay, so there exists a counterexample such that a squared plus b squared equal to c squared, and a is odd and b is odd. Okay, so now we want to show that this counterexample leads to a contradiction. So now we are going to use this as my hypothesis. So by definition of odd number, because a is odd, b is odd, so we have a is equal to 2k plus 1 for some k, and b is equal to 2m plus 1, again, for some m. Okay. And because c is an integer, there is two cases. Okay. So first of all, if it's an integer, it can be odd. So case number one is if c is odd. Okay. So if we assume c is odd, that means c is equal to 2p plus 1 for some p. Then c squared is equal to 2p plus 1 squared equal to 4p squared plus 4p plus 1. I'm going to factor things out. This is equal to 2p squared plus 2p plus 1. Okay. And of course, by closure property, this thing is integer. So c squared is 2 times some integer plus 1. So c squared is odd. Okay. But now c squared is equal to a squared plus b squared. And both a, b are odd. So I can express it 2k plus 1 plus 2m plus 1. And I'm going to expand it. And then you're going to combine and factoring 2 out. You get something like 2 to the power of 2k squared plus 2k plus 2m squared plus 2m plus 1. Again, by closure property, this thing here is integer. So you get c squared is even. And now you have arrived at a contradiction. Okay, so this is a contradiction. So that's case number 1. But you also need to do case number 2. Case number 1 is when c is odd. Now if c is even, we're going to do the same thing, except that this has become a little bit tricky. Okay, so when c is even, you're going to say c is equal to 2p, and then c squared is equal to 2p squared, which is 4p squared. Okay. And now, as before, c squared is equal to a squared plus b squared. Remember, both a, b has to be odd. Again, we're going to do the same thing as before. Before I have this thing here, so I'm just going to copy it. Just substituting 2k plus 1 squared plus 2m plus 1 squared. In this case, my factorization is slightly different. So 4m squared plus, 4m plus 1 plus 4k squared plus 4k plus 1. Factor out 4m squared plus m plus k squared plus 2. Okay? So here is the most tricky part, and it's similar to what we've seen in a recitation, but when you have the first line, when c squared is equal to 4p squared, that means c squared mod 4 is equal to 0. Okay, that means the remainder of it is equal to 0. But when c squared is equal to 4 times this plus 2, when I take mod 2 is equal to 2. So this is a contradiction. So in both cases, that it leads to a contradiction, which means the counterexample doesn't exist. Okay? But here, this is sort of the, if you want to read about it in detail, here is the clearly written out proofs. Okay? All right. Now let's look at sets. So first practice problem, give you a set of A. What is A? A is a set of all even numbers. We want to describe z minus A. So z is a set of integers. Z minus A is every integer that is not even. So what does that mean? It's a set of odd integers. Okay. So A is equal to 2x, x in z. Okay. Z minus A, as I said, is a set of odd integers. So that is equal to 2x plus 1. This is my way of describing odd integer. And the first part is, the one that's hidden a bit. You may or may not need to put it there, because by closure property, if x is an integer, 2x plus 1 is an integer. But this is really talking about its domain. Actually, let me correct it. So this part is talking about the domain. This part is talking about the predicates. Okay. Now let's talk about Venn diagram. So we've seen some Venn diagram in the part 1. We're going to do more. Okay. It says whether or not. So what you're going to do is you're going to do Venn diagram on the left and Venn diagram on the right, and to see whether the diagrams look the same. And this is a good time to pause the video. Okay. And now I'm just going to go through the solutions. So let's do the left-hand side first. I have three sets, A, B, and C. I'm first going to do B union C and see how it looks like. So BC, and of course I'm going to show the universal set. B union C, I'm going to color it by yellow. So that is everything in B and everything in C. So everything in B and everything in C. Right? Now, on top of it, I want to take this, intersect with it. With B union C, take A, intersect with it. So now I want to construct A intersect B union C. Then you have A, B, C, U. Okay, so now when you take the intersection, the set shrinks. So what you get is this tiny piece right here. That is A intersect B union C. Okay, this is a slightly nicer drawing of the picture I just drew. Now we're going to do the same thing, and I'm going to omit this step. Let's just look at the pictures. Next thing on the right-hand side, I'm going to take A union B, A intersect B first. So that is this part. Well, let's use a different color. Right, this is the same yellow part. But now I'm going to union C, so I get what's drawn on the right. So in some sense, now if you compare those two, this is the left-hand side looks like, this is right-hand side looks like. Of course, they are not equal. So this is actually not equivalence. So the statement is false. So now the question is, can we think about a counterexample where, of course, this is not true? If I have the set A, B, and C like this, where A is 1, 2, B is 1, 2, 3, and C is 1, 2, 5. If I look at this, the left-hand side is B union C first, which is 1, 2, 3, and 5, intersect A, that is equal to 1 and 2. Of course, on the right-hand side, if I take A intersect B, that is 1, 2, and I'm going to union C, that's going to be 1, 2, and 5. So of course, those two sets do not look the same. Okay. All right, let's do another one, Venn diagram. I'm going to do A, B, and play with the complement. So recall the complement, if U is my universal set, then A complement is equal to U minus A. Okay. So first of all, on the left-hand side, we're going to do A union B complement. But first of all, I'm going to do A union B. So if this is A, this is B. Oh, A, B. So A union B is going to be the yellow part. Okay. And I'm going to take the complement, which is everything outside of this part. So A union B complement is actually U minus A union B. So it's everything outside. Okay. Of course, I want to label things. So that's the left-hand side. And if I do right-hand side, I'm going to do A complement first. If this is A, and this is B. A complement is essentially everything outside of A, regardless of how B behaves. This is just everything outside of A, which is U minus A. Now we're going to do, again, B complement, which is U minus B, which is, again, everything on the outside of B. Oh, let's use orange. It's A. And now finally, we're going to take the intersection of those two. So remember, I'm taking the intersection of the colored area. That's look like this. All right. So as you can see from the diagrams, the left-hand side equal to the right-hand side. Okay. So this is just extra space for you to practice on your own. So this is just a quick review. We kind of did this for part 1 already, but just to recall that we use n of A to denote the size of a set A. The next quick review is inclusion-exclusion principle that we also went through our example, but it's very important to remember. If I take the size of two sets union, it's equal to the size of each set minus the size of their intersection. But if I have a three-way, when I take each set size minus the pairwise intersection, I need to add the triple intersection because I'm too aggressive in terms of subtraction. I need to add back a copy, right? Remember the picture we had where if you have three sets, all this area has one copy, all this area has two copy, the middle has three copy. When you extract three copy, you didn't count the middle, so you need to add it back, okay? So we kind of went through this example. Again, it's a quick review. In this case, the set A is a set of y between 1 and 1,000 that is divisible by 2. And then I have a set B that is divisible by 3. And then the set A intersect B is a set that is divisible by 6. So the idea is to compute, if I want to compute the union of those two, it's using inclusion-exclusion principle. Right? Include each set, exclude their intersection. And then this is what you get here. Similarly, we have a slightly more complicated one. Again, this is a quick review. If I have three sets, okay, where this is set A, set B, set C, then I need to think about not only each individual set, how many elements are there, but their pairwise intersections. In this case, pairwise intersection of A and B are the numbers that is divisible by 6. Similarly, the intersection between 3 and 5 are the ones divisible by 15. So you can do this to look at, of course, the last one is the three-way intersection of those three sets are the ones that is divisible by 30. Okay. Again, if you have not tried this on your own, please do this before looking at the solutions. So this is a quick review. Now let's look at sort of set definitions, especially set membership. Recall this symbol means it's an element from the set. This symbol means it's a subset. This means it's a proper subset. So now I have three sets, two set A and B, each has three elements. So the first question is empty set an element of set B? Okay, again, please pause the video and then try to solve this on your own and then compare your solution with my solution. So here, first question is empty set an element in B. B has three elements, C, D, and E. Empty set is not one of them, so the answer is no. Now the question is, well, A has, is element A part of B? Again, the answer is no, because B contains only three letters, C, D, or E, none of them equal to A. The third question is empty set a subset? Remember we learned from part 1 of the lecture that empty set is a subset of any set. So this answer is yes. Now, what is the size of B? It has three elements. What is the size of A union B? First of all, let's compute A union B. You look at unique element. So first you can do three elements, and then you remove the duplicates. The C is a duplicates. So this is size 5. Are sets A and B disjoint? We know there's a duplicate because if I take the intersection, they share element C. So they're not disjoint. Disjoint means that their intersection is empty, right? Okay. So that's just the answer. It's important for you to quickly review what is Cartesian product. So if I have two sets A cross B, that's a Cartesian product. The element in there is pair of element where the first element coming from set A and the second element comes from set B. Okay. Now n tuple is you have let's say you have n set and you choose an element from each set. So another way to think about it is for n is an integer, n is bigger than 1, I'm going to choose element x1, x2, xn, where xi is part of each set, is xi. So you choose an element from each one. But n tuple is n such numbers. So now let's begin to look at Cartesian product of sets. So in this case, we're going to ask you to list elements. For example, in this case, what is A cross B? I want to choose an element from A and an element from B. So there is actually a mental picture you can draw. Let's say this is my set A. It has three elements, 1, 2, and 3. I have a set B. It has two elements, X and Y. X and Y. Okay. And then the way we do it is I pick an element from left and pick an element from right. Element from A and element from B. So each time I pick a pair, I draw a line. So essentially, you're looking at a complete bipartite graph. Well, you drew all possible edges from left to right. So 1x is an element. 1y is an element. 2x is an element. 2y is an element. 3x and 3y. Essentially, we want to look at all possible combinations of choosing an element from A paired with an element from B. And also it's ordered, right? The element from A shows up first, element from B shows up next. Now we want to do A, B, and C. We can do the exactly same mental picture. I have 1, 2, 3 from A. I have X, Y from B, and I have just the color blue in C. Again, what I can do, I can choose 1 and goes to X, goes to blue. 2 goes to X, goes to blue. 3 goes to X, goes to blue. 1 goes to Y, goes to blue. 2 goes to Y, goes to blue. 3 goes to Y, goes to blue. So essentially, for this solution is I just add an extra blue for each element. So 1X, blue, 1Y, blue, 2X, blue. Each element is a triple. 2Y, blue, 3X, blue, and 3Y, blue. So what is A squared? Remember, A squared means A cross A. So 1, 2, 3. 1, 2, 3. And you're just going to connect all possible pairs. 1, 1, 1, 2, 2, 1, 2, 2. 1, 3, 1, 2, 3, 1, 3, 2, 3, 3. Okay, so this is all listed right here. Okay, so remember when you do that, when you have Cartesian product, you choose one element from the first set, one element from the second set. So what does a set of sets looks like? Remember the mental picture is it's a box of boxes. Okay, it can be a box of boxes as well. And what is a power set? A power set of a set A is all possible subset. Okay. So now the next question we want to ask. Oh, actually, it's just a review. Again, we want to look at what is a partition. And if I have a set A, a partition is a set of sets such that each of the set is empty, pairwise set, non-empty intersection, and the union is equal to the original set. So again, example, if I have a set P, which is A, B, C, D, E, then for example, S, which is equal to A as a set, B as an individual set, C, D, and E. This forms a partition. However, S prime that has an empty set in here this is not a partition because it does not satisfy the first condition. So you will see a few proofs that involve in using the property of a partition. Either you prove something forms a partition or something does not form a partition. Okay. And finally, if you recall, when we think about sets of sets, if we look at a set like this, this is a set of sets. The set 1, 2 is actually an element of this set. So it's very important that it's an element, but it's not a subset. Okay. And the power set mathematical formula is it's all set S such that S is a subset of A. And always remember, empty set is always an element of the power set. Okay, so that's it for the second part, and I will see you in the recitation to do more practice problem involving sets.